Next speaker is Wodson Mendson. We talk about foliation with small singular set in arbitrary characteristic. From University of Fluminense.
Okay, thank you for the introduction. Can you hear me? Yes. Okay, I will talk about foliation with small singular set in arbitrary characteristic. So this is a joint work with Thiago Fassarella and João Pedro dos Santos and Frederico Tuzé. So I divided my talk in two parts, and the first part I will introduce the objects and the problem that we are interested in work. In the last part, I will present you some results that we have. So let's go for the introduction. K, in this part, K you denote an algebraically closed field of characteristic P, and X denote a smooth projective variety defined over this field. And the condimension Q foliation is just a covariant subshift of the tangent shift of the variety with this rank that has these properties. So it's closed by the Lie brackets, and the quotient is torsion-free. If the singular set is defined, the set of the points show that the quotient is not free, or X modulo. Okay? So we have a class of foliations. In this class of foliation, we can look for the subclass of that foliation that is algebraically integrable, that is given by this definition. So you take a variety X in the F foliation. We say that F has a rational first integral, or is algebraically integrable if there is a rational map show that defines the foliation this way. The foliation is given by the kernel of the differential map. And here I have an example. So you take a foliation P1, P1. You just take the first projection. The variant curves of this foliation is just the fibers of this map. Another example is what you call the rational foliation, Pn. So you take a bunch of polynomials of the same degree without common factors. You consider this one form, is Q form here, given by the contraction of the radial vector field with this Q plus 1 form. And this foliation is algebraically integrable and is given by this rational map. Just the components is the FEI. Okay? So the main problem is give you a foliation, you determine a condition to ensure that F admits or not rational first integral. The first theorem that I learned about this is the Bougeot-Nolot theorem. So you start the codimension 1 foliation in smooth projective variety defined over a very complex field. And then algebraically integrable is the same to say that foliation has infinitely many invariant hypersurface, algebraic. Like we have this famous example of Bougeot-Nolot. So the Bougeot-Nolot proved that this foliation does not have any algebraic invariant curve. So in particular, we don't have a rational first integral for this foliation. So we have also this theorem, so that gives you a numerical condition to ensure that the foliation has a rational first integral. So you take X, a smooth complex projective surface, and suppose that the canonical bundle is not pseudo-effective. This means that there is an ample divisor that intersects negatively. Is a negative number, the intersection of the key F with this ample divisor. Then the foliation has a rational first integral. When the X is a rational surface and the F is irregular, we can show that the canonical bundle is not pseudo-effective. In particular, we have this theorem by Brunella that say that the rational complex surface, if you take a regular foliation, then this foliation has a rational first integral, has infinitely many invariant curves, algebraic invariant curves. And we also have this conjecture by Tuzé. So you take a regular foliation, rational connected variety. This means that you're giving you 2 points. You can join these 2 points by rational curves and change of rational curves. Then F is algebraically integrable. Related to this kind of problem, we have two theorems. This one by Druel, that we say that if you have a weak Fano manifold, weak just means that the anti-canonical is F in big. And F from regular foliation in X, then the foliation is algebraically integrable. So you have infinitely many variant algebraic hypersurface. And we have this theorem by João, if you consider the threefold case, and just ask for the anti-canonical snap, then I'm sorry. You take a regular foliation X, then the foliation is algebraically integrable. So, and we can ask you what happens when the characteristic is P. So we have the same. The problem is algebraic, so you can ask over any field. So for this, I'll introduce to you the notion for pre-closed foliation. We fix now the K algebraically closed field of characteristic P. And take a foliation of the variety X, find out of this field. We say that the foliation is P closed if you're looking for the tangent sheaf. This guy is closed by P powers. You take a vector field, you take a P power that is vector field. This is still, we still have a derivation, and we ask for this derivation to be part of the tangent sheaf, the foliation. The algebraic condition essentially is this here. You take a vector field that is tangent to foliation, then the P power for this derivation is also tangent to the foliation. And we can check if you have a foliation that has a rational force integrable, then the foliation is P closed. And here, just an example, it's the simplest one. So you take this one form here that's defined the foliation P2, and you can check that the foliation is P closed if and only if alpha is an element of the base field, FP. Okay. We have also this theorem which says that P closed is the same as algebraically integrable. So foliation is P closed if and only if it is algebraically integral. And we also have a Darboux-Jeannot type theorem for characteristic P. So if you have a codimension 1 foliation, F is algebraically integrable if and only if admits infinitely many invariant hypersurface. Now I move for the part of results. I will present you some results that we have. Denote K by algebraically closed field of characteristic P, can be 0 not. By small singular set, I mean in some cases that the codimension of the singular set has codimension at least 3, or the set is empty. Here I have this first proposition. So you take a foliation of codimension 1 Pn given by a projective 1 form. Suppose that the singular set has codimension at least 3. Then the form defined the foliation is closed. This does not happen in characteristic 0, because in characteristic 0, we always have a component of codimension 2, or codimension 1 foliations. So this is particular for the characteristic. This condition codimension at least 3. The idea is just apply some division lemma in the integrability condition, and you're looking for degrees and arrived in this condition here. As a corollary, we have this. So you take a codimension 1 foliation Pn. If the singular set has codimension at least 3, then P is positive, and P divides the degree of the normal bundle. We also have some restriction when we look at foliations that has this small singular set. So for surface, we have this theorem. So you take a regular foliation in small projective surface defined as X, and then we have this product, the self-intersection of the normal bundle is 0 in this field, base field. And I present you this theorem. So this is related to the Bombot theorem. That is more general, but this is a particular case. So you have a regular foliation, is more complex projective surface than the NF times NF is 0 in the complex number. Here, just a remark that there are, for example, we have examples of irregular foliations in characteristic 2 specifically. That this guy is not 0 when you look in the integer ring. This is a number, this is not 0, but it's multiple of P. And we also have this restriction. So you have a regular foliation on a smooth projective surface. Then we have this formula here. which compare this intersection with the second Share class of the surface. The idea, the proof is just expand this formula using the relation with the first class shared classes and so on. But we can use this to check that in P2 there are no irregular foliation, for example. Here's a theorem about regular foliations on minimal rational surface. So you take a regular foliation minimal rational surface, X. Then the surface is a Heisenberg surface, with E is different of 1. And the characteristic is bigger than 0. And F is the fibration given by the surface to P1. Or the characteristic is P, and P divides the E. And F is a Cartesian foliation given locally by this guy here, in this form. Where this guy, Z is the coordinate of the fiber, and this guy lives here. As a corollary, we have this thing here. So any regular foliation on the minimal rational smooth surface of a algebraically closed field of positive characteristic is P-closed. So is algebraically integrable in the characteristic P. If we are in this situation, we have this first class here. We can show that we're still here. We also have a regular foliation del Peso surface. So this is its theorem. So you take a del Peso surface, the anti-canonic example, and over algebraically closed field of arbitrary characteristic, and take a regular foliation X. Then we have this characterization. X is the P1 times P1, or the blow up of P2 in 1 point. And F is given by the fibration to P1. But as a corollary, we have this. So run the regular foliation on this smooth del Peso surface of algebraically closed field of positive characteristics P-closed. Is algebraically integral in characteristic P. Okay. I'll give you an idea of the proof. I will not enter in details of the proof. So the idea was the following. So you start the regular foliation on X, and we use the structure of the cone of Morricone of X, that he has a finite type. We can write in this way, where Ci are rational curves, and we have extremal rays. And we have a classification. So X is P1 times P1 is the blow up of some points, at most to 8. And the CR is smooth rational curves. We can show using intersection formulas that this guy is in F, the normal boundary is in F. It's sufficient to look for the H generator. So we consider cases where this curve is invariant or not. And you conclude that this guy is in F. And we suppose that we are in the case where we have at least 2 points in the blow up. So these curves are -1 curves and cannot be invariant by F, because there is a invariant of Camacho-Sad formula, which say that the self-intersection of any invariant curve should be 0, mod P. In the last step, we compared the canonical bundle with its generator here. So we have this inequality. So this guy is F also. And this implies that we have this, but we saw in the previous slides that this guy is negative, because we are in the blow-up of P2. So you arrive in a contradiction. So we have 2 cases, just P1, P1, or the blow-up of P2 at 1 point. And we classified this in the minimal rational case. So we have the result. Okay, I finish presenting you some results for the regular foliation projective space. We have this theorem here. So we characterize regular foliation projective space and the characteristics. So if F is regular, we can show that the codimension is 1, the characteristic is 2, degree is 0, and n is odd. So, and we can say more. Globally, the foliation is given by the f, where f is homogeneous of degree 2. So I will not give you the proof, but the idea is is to observe that the subbundle gives you a nested map to Pn to the Grassmannian. And we use this nice theorem here, which say that if you have a algebraically closed field and you nest algebraic map, then n is odd and the Q is n minus 1. So we are in codimension 1, and there is some work to do to show that in the codimension 1, in characteristic 2, we have the characteristic 2 in the explicit form here. So I just put the parts of the theorem. Here's another theorem. So we take a foliation, codimension 1 foliation with singular set small. So we have seen that the P is positive, P divides the degree of the normal bundle, F is given by a closed form, and we can say more. F admits some reduced invariant hypersurface, and this guy is exact. So there is homogeneous polynomial so that this guy is the differential of this polynomial. So this is equivalent. So you have just one invariant hypersurface ensure that this guy is exact. As a corollary, we have this. So this foliation admits just one invariant hypersurface if and only if admits infinitely many. So I will finish by presenting you the interesting example. So this is a codimension 1 foliation in P3, in Pn, that has this degree, 2p minus 2, that has finite singular set, but we can show that this guy has no algebraic invariant hypersurface. This is nice, a curious example because we have this. So if you assume that P does not divide the degree of the normal bundle, then F admits at least one reduced invariant hypersurface. So I'll stop here. Congratulations, Frank. Thank you for your attention. So.